Hello, everybody. This is Lakshmi, first year PhD student at University of New Hampshire. Today, we are going to talk about BGP. So I'm going to start with the introduction or by giving a brief overview example of what a BGP does when you try to access something through internet. BGP is just like a postal service where it acts as a routing protocol at each and every router that hits in between the source and the destination. For example, if we have to request something to Facebook, like www.facebook.com, it actually starts searching for the nearest routers possible. So first, the UNH network will hit the nearest ISP. Let's say it is ISP 1. And this ISP, in this ISP, that particular BGP protocol will actually look for all the possible paths for UNH to reach Facebook by looking at its routing protocol. And once it finds the best path, it will figure out, okay, you can go to ISP 2. Then the message travels from ISP 1 to ISP 2. And once it hits ISP2, ISP2 does the same again. Like every router, since every router has a BGP protocol, the protocol will look for its surrounding paths, which can reach to Facebook in an easiest way, and decides, okay, it has to go to ISP4 because it is just one hop. And when it reaches the ISP4 is the person who contacts with the Facebook. So this is how actually www.facebook.com website is shown on our desktops. So in this process, they have to have some agreements because all these individual clouds are called autonomous systems. And these autonomous systems are independent to each other in a different ways. Because they have their own implementation, they have their own functionality and all, but they have to get into an agreement when somebody is reaching out, hey, I want to go to Facebook. Then so they have to actually have this peering agreement among themselves so that they give advertisements every time periodically telling that, okay, my incoming or inbound or outbound routers are working fine, or nothing is changed, or something. If something is changed, oh, I cannot work anymore. So maybe you have to find somebody else to travel to Facebook. So in order to provide these advertisements, they have to have this peering agreement. And this is what makes BGP special, because every time a new system is added to the existing network, it is very easy to scale it to users' demand by just adding that particular autonomous systems routing updates to the existing routers. So the existing existing topology is not changed that much, except for the fact that an additional effort needs to be put in that getting added autonomous system to communicate with the existing network.
So these announcements, they carry they tell you that, hey, you can reach this address from me, right? So it's not just about the health of the AS, it's about what is reachable from each particular AS.
Yes, so they are aggregated in such a way. For example, if Facebook has 10 servers that are actually connected to nearby, it is more than 10 in real time, but those 10 servers are actually open to any of the other requests from any other autonomous systems. So ISP4, for example, has the information of those Facebook's servers, and ISP4 to which autonomous systems it is connected to will have the aggregated data of all the routing information with ISP4 and Facebook. And ISP1 will have the aggregated information of all the ISP2, ISP3, ISP4, and Facebook. So this is like a cumulative thing. Every router will have the information of each and every other router. That's how when UNH reaches the ISP1, it knows that, okay, I think I found a path from ISP2 to ISP4 to Facebook, and travels the message. And this is the brief summary of BGP protocol. It is a routing protocol, so it is located at each and every router to just route the incoming packets and route it to the appropriate path to reach its destination. And it meets the increasing client data, implying growth of the data centers, and interconnects autonomous IPs on the internet. It also supports large topologies compared to others instead of like just the traditional topologies. It can be extended to any of the modern topologies. And it runs on the top of TCP layer, which is used by many services. So it is very flexible for most of the applications that are out there. But it has some problems, even though it is much more scalable and all. It has some convergence issues and routing instabilities occurs because you don't know when or how hardware failures happen. And there are some frequent misconfigurations you can observe in this. So let's get into deep about these problems and see how Facebook is trying to solve them. First problem is BGP convergence problem. This is also called as a path hunting problem because whenever ISP2, for example, wants to get the information of ISP3 and ISP4, ISP3 may not be directly connected to ISP2, but it has to get the information of ISP3 since it is connected to ISP4. Because ISP2 on a whole has to have the aggregated information of all the routes that are existing to define the best route. Sometimes what happens is ISP3 may not be able to send the information correctly, like, okay, some of my routers are not working properly. If that update is not sent to the ISP2 properly, then it could, ISP2 don't know about that breakage, and it could just send the data as it is, and it might create a problem. And also ISP2 is not working at one request at a time. It has to take like so many requests at a time from ISP3, ISP4, ISP5, etc. So it has to get all these updates and make them into a single data so that it can update its routing table. So some problems might happen when it is trying to actually get the data from different ISPs at the same time and converge them into a single routing table. And the second problem is called routing instability problem. This is where most of the hardware issues come into place, like depending on how many years it's been running from, and depending on what kind of crashes it is happening. For example, if a router is replaced from its old router to a new router, it should actually show something. It should actually return something saying a diff. That is one of the pathological messages it displays. Oh, now we have a new router, and the new router doesn't know what the existing protocol is. So you might have to update it, which is a cool feature because most of the tools nowadays use this kind of tools to actually know what is causing the problem in the routers. But it's still, there is a problem with routers over the period. And it also affects how the routes are getting updated, like how the updated information is getting transmitted across routers. So this is still a problem. And misconfigurations happen when it actually cannot update the inject the prefixes properly. For example, ISP3 is trying to send as path attribute, which is a normal I think it's a generic attribute that is used to send this is my update or something like that. So if ISP3 is sending ISP3 and ISP4 information to ISP2, which means that ISP3 is connected to ISP4, but in future, if something happens and it was not like ISP3, there is no more connection between ISP3 and ISP4, and it is trying to send that update to ISP2, if there is a problem in transmitting that information at the router side or in the transmission side, it could create a problem. These three actually sum up into one common problem, like what if the updates doesn't go on well properly, or what if the BGP protocol itself is not able to handle the incoming updates properly. So these BGP problems may affect Facebook, such a huge company with all the heavy client inflow. So they modified BGP into something else, and they added some additional components to it to make it more customizable and flexible. So the things they followed here are uniformity and simplicity, even though how hard it is for them to maintain the inflow of the increasing clients. They had to follow the uniformity and simplicity features across all the designs, like topology design or the AS numbering scheme they had, and then the routing policies and the operational pipeline, even the testing pipeline. So let's see what their network topology looks like. So their network topology has.
So quick remark here, right? So Facebook BGP, like we're no longer on a like public internet, so they employ BGP at the data center level, correct?
Yeah, they have their own customizable BGP agent implemented. And so this is a kind of topology they are using. This is not star or this is not hierarchical. It's something modern because each and every data center has so many of these server pods, and each server pod is having fabric switches and rack switches, and servers, the main servers, are actually connected to these rack switches. And the design is such that the rack switches are connected to each and every fabric switch in that pod. And the fabric switch is actually going outward of the server pod to a spine plane and connecting to all these switches in the spine plane. And the number of switches in the spine plane depends on how many fabric switches we have. And these spine planes are actually acting as the carriers for transmitting data between the server pods. So the server pods didn't have any direct connection between them except for passing through the spine planes. And this provides redundancy in such a way that if a switch fails, the other switch works for the same spine plane or for the same server pod. So they'll be in good shape, even though most of to some extent of the switches fail at the same time. And it is very difficult for them to actually accommodate the resources with respect to their IP addresses or something. So they have a customized autonomous system numbering for each and every switch. So each and every server pod is considered as an autonomous system. So it is given a number. And inside this server pod, each and every rack switch is given a number, and each and every fabric switch is given a number. And so these are all converted into one atomic system number, and then the spine plane is also having the same AS number because it has to ensure that no router is actually routing through more than one spine plane. So it is with fault tolerant checker. So each and every spine plane and server pod are having their own AS numbering schemes, and they are actually communicated using those numbers. Whenever a policy is implemented on them, they apply it with respect to the AS number, which makes it easier for them. And coming to their routing policy goals, so they have all the things implemented to achieve this reliability, maintainability, scalability, and reachability, because the statistics, they show that there is so much increase in the last, for every year actually, the users are gradually increasing. So their design should be in such a way that it can be easily upgraded or easily scalable. And they have to make sure that the routers are in good shape all the time. And they have to make sure that if dynamically, if some router changes, then the BGP protocol should be able to recognize that change and direct the client's message to another path, even though it is longer, appropriately. So coming to reliability, this is related to the convergence problem we have discussed. For example, if a fabric switch wanted to connect with the rack switch and there is a link failure, then it has to go through all the longest path, like to RSW2 and then to FSW2 and then to RSW1. But if what happens if there is no link at all between the FSW1 and RSW1? It has to again go through the longest process to give the advertisements like, okay, these are the connections I have. So if you follow these connections, you can reach me. So that kind of message, it has to follow all this long path to FSW1. And they are using.
So there is this short path, right? So the red arrow is the preferred path, right?
Yes.
And I believe the paper mentions that in addition to this, the shortest path, they advertise a backup path.
Yes. Yes.
But they don't try to advertise all backup paths, I believe, right? Only like one.
Yes.
Yeah.
So, for example, so backup path actually happens predeterminedly, like even before the message is traveling for each and every switch, they calculate the backup path. So what happens? So they take the combination of what happens if this link fails or what happens if this link fails, and they try to make sure if there is another path. So that is the backup path. That is how BGP can make sure even though that link fails at that point dynamically, it can transfer it to the longest backup path.
And because the backup path is advertised ahead of time, then there is like very little downtime, right?
Yes.
So if you detect that the link
this is all
failed, you can just follow the backup, correct?
Yeah, this is all predeterminedly calculated even before messages are starting to flow. So they have everything in the database and BGP will access it as it needs. In order to provide the advertisements, they are using these match and action tags. These are nothing but like if conditions. If it matches the particular tag, it performs the action and forwards the message to that particular action item. For example, if RSW is having rack prefix as its tag, then when it is going to FSW2, it matches with the rack prefix tag which it came from, and then it will decide to which tag it should go to next. So which is here backup path, and when it will decide like, okay, RSW2 has a backup path as its match, so it will send to RSW2 and then performs the action. So it sends it is sent from RSW2 to FSW1. So these advertisements are really important because if these advertisements didn't happen properly or not predetermined in any way, then there is a problem that FSW1 no longer knows what's happening in the rest of the system recently. So it will just think that everything is normal and try to send messages, but it is not the case. So that is very sensitive thing in BGP protocol. And for maintaining their switches or switches, they actually have 3 different states for each and every machine, like live, drained, and warm. If a machine or router is working fine, they give it a live state. And once the router is acting up and it is very hot, it just goes into drained state. But in between the process of going from live to drained, it will be in warm state just for the maybe for some monitoring kind of thing, like, okay, these many routers are in warm state now and they can soon go into drained state. So it is easier for them to actually think of any other alternative, like how to reconfigure everything or replace everything. So scalability and reachability are 2 other items that they talked about in the paper. They wanted to make sure that all these aggregation of transfer of the routing information from one router to another router they are referring to that as the hierarchical route summarization. So each and every route has the summarization of the routing information of the other routes, and which will be helpful when you try to scale the existing network. If you are trying to add one more server plane or spine plane or one more server pod to increase your network capability and bandwidth, you can actually add that server pod and then try to communicate with the existing network. So you're not changing anything in the existing network, which makes it more scalable in less time.
So from the spine plane view, right? If you add a server pod, that's pretty much just adds in one more thing to the routing table, right?
Yes.
And how the things are being routed in the server pod, that's like on another level of this hierarchy. So that's what they mean by the hierarchical, whatever it is.
Yeah, so every time there is a router, it actually has the information, getting the information of the other router paths. And so reachability, for reachability purposes, instead of using these hardware components, they use virtual IPs. And they have this VIP injector to actually scale to more devices, to more VIPs whenever there is a demand, and act appropriately. So this is how they're making sure that even though when there is a high time during the day, okay, or particular occasion, if somebody are actually accessing Facebook so much, this is how they are able to make sure that everybody are able to reach Facebook. And all these policy goals they have are almost stable all the time, because every time they are trying to implement something new, it is less than 8% that they are making changes to the routing policy, because they have a template which is generic to all the data centers. And whenever there is an up, and these data centers have different platforms. Some may have different platforms. So whenever there is a upgrade to these policies, they just update the template, which will in turn automatically update the policies, which is really helpful. So that's how they're making sure that this is very simple and everything is uniformly acting. And in order to meet this uniformity and simplicity, they also made sure that they are having very limited feature set. Instead of going beyond whatever they can do, they are making sure that they design and the policies are matching with each other according to the features. And multi-threading is should be like multi-threading is an important factor, because BGP will not communicate with one router at the same time, because it has like so many routers around it in the network, and it has to grab all these periodic updates from each and every router. So it should be multi-threaded. They performed an experiment on like comparing all these different BGP implementations like Quagga and PERT, or also other BGP implementations. But FP's BGP had really good, like very less convergence time, even though the number of routes are increasing. So that's how they were able to prove that their BGP version is the best. And similar to that, they have this policy cache. Whenever a policy is executed across a router, they don't need to actually execute it to each and every router, because they are following certain rules, such as if all these routers are in a peer network, then all these routers will have a same BGP attribute going executed. So with the help of that rule in mind, they were able to execute one policy on one peer and save that result in some policy cache, and use the same result on other peers without re-executing or recomputing. So that's how you can see that as the number of routes are increasing, the process time for the routers are very low compared to the traditional no cache BGP version. And in order to maintain the system in an efficient way, they have a testing pipeline. So first they do unit testing, which we all know, and then they go to emulation testing, where they check for failure scenarios. And then once it passes the emulation testing, they go to canary testing. And here everything is tested, which is not tested beyond, like just not tested in emulation. And this is basically the production testing. And they check multiple features here. And once if everything is green and certified, they go to deployment. So deployment at Facebook happens in 6 phases. So these 6 phases are actually increasing. Each phase is, as you go to 6th phase, the deployment size increases because they have to make sure that they are not crashing anything when they're just trying to deploy the whole 100% onto all these data centers across the globe. So here is a little diagram that shows a timeline of their deployment over 12 months. For each and every month, you could see how the 6 phases varies, and each and every each and every deployment, you could see that the 6th phase is more likely the biggest one, because it's the major, like 80% of the deployment happens in that. So, and they also had this error percentages rate for each and every release, how many errors are happening for across each and every phase. Obviously, the phase 6 is having more error rate compared to other phases. And in the paper, they also discussed about the unavoidable obstacle, the network issues, which we can't predict how or when it will happen. So they have these site events located in each and every router. So whenever there is an event that is triggered, they will. They are having these monitoring tools to actually see how much network outage or damage is happening, and then act accordingly. So these SCVs can trigger for anything. It's not only for network issues, they can trigger for normal code bugs or incorrect order of some pushings and version incompatibilities. So they basically monitor any slight deviations in their network and monitor using these tools like NetSonar and NetNorad, and act accordingly. So this is how generally Facebook maintains its protocol. So if you have any questions, like I can answer.